All right, live stream running. Everyone here? 1 minute passed, pretty good. That's mostly to myself, I guess. Yeah. Yeah, attendance code, but that's the one I wanted to show again. So just a little recap. We talked about this last time at length, but to refresh everyone's mind after the weekend and all the garbage collection it may have brought, we looked at this graphical representation of compression, the Lempel-Ziff-Welch algorithm, or more generally, the Lempel-Ziff family of compression methods. And here you see in the example, there's boxes with pointers to previously used boxes. And that's pretty much what Lempel-Ziff is about, finding things that occur now that have occurred before. And so instead of writing it down another time, you just reference where you've seen it before. Then we had a long example of how this works in practice. On some example. And you saw how the dictionary on the right here fills up with things over time. Because whenever you encode one phrase, you add one new phrase to the dictionary. So just to pick one example out of those again, we had the text encoded up to this point. And now the next thing we're looking at is starting with U. So we try to find the longest match that we have in our dictionary. These are all just single letters, but we've built up a few longer ones in the right column. In particular, we found U. So we use that. That's our output. The number, the code word for this string, or the code for this string, is what we put in the output in the coded text. But then after we're encoding this part U, we save something new in the dictionary, namely the previous phrase, the thing that we could find earlier, plus one more letter. And that way we keep growing this dictionary with new and longer strings as we keep going. All right, many more steps. And we finished with basically this code that puts the same process you've seen in the example into pseudocode. And I talked a little bit about why you want to use a try for representing the dictionary, because that makes these steps fast. Pretty much that's the key step, that a try supports in constant time, and other data structures is not so clear how to get it fast. All right. Any questions up to this point? Then we should have a look at how to decode that again, because compression is only useful if you can invert it. After we've seen how to encode with Lempel-Ziff-Welch, we now want to decode, the decompress step. And in principle, it's easy. We have to reverse what the encoder has done. Otherwise, we don't get back to the same source text. The details are a little more tricky because, as we'll see, the decoding is always a bit lagging behind. And the intuition behind that is easy. Remember, we always encode one code word and then store a new one. And so we have to do the same in the decoder. So the normal mode of operation is we decode a substring from the source text, which we find as a fixed length code word. So the splitting of the coded text into code words is easy. It's always, in the example, the slide said 12 bits is a typical size. In fact, it's a parameter you can often play with if you use zip programs. So there's a fixed length code word, so it's always clear what the next code word is in the coded text. And hopefully that maps to something in your dictionary, so you can decode that code word to something in the clear text, in the source text. And after we've done that, we have to add a new string to the dictionary, because that's what the encoder did, and we have to keep adding these because they might be used in the future. And just for notation, I'll always use y for the thing that we decoded, and then x with c added as the thing that we add to the dictionary. And now the trick is that in the encoder, x and y was y and x was basically the same. But now, because we're lagging one step behind, x is the previously decoded thing, right? Remember, we can only store the new thing to the dictionary once we know what it is. The encoder encoded one step and then added that thing to the dictionary. In the decoder, I can't really do that. I first have to decode the thing before I can add it. And so the easiest way to deal with that is to say we decode one thing and then add something, but what we add is actually the previous string. So we'll have x as the phrase that we decoded in the last step, y the phrase that we decode now, and xc, this one more letter that we should add, is actually the first character of y, because that's the new phrase. So here's a concrete example that may make it more clear why we have to do it this complicated way. In the previous case, in the previous step, we decoded x, and that was ban. Now, the encoder would have added ban plus the next letter to the dictionary. But at the point of decoding ban, we don't know what a is. We don't know what the next letter is. We haven't seen that a yet. So we have to wait for the next step. When we decode y, which is an in this case, then we know the first letter of y was an a. And only then can we add xc to the dictionary. Okay? That's the complication. We're always lagging one step behind because we need this first letter of the new phrase. So we can also only start adding after we've seen two phrases decoded. We can't start earlier. Clear so far? Let's have an example for that as well. Similar setup, but a different string so that it doesn't get too boring. So what we get is a sequence of code words. Now these are written in gray. They will come up highlighted later on. We start again with filling the dictionary with all the single characters in our alphabet. That's the same as before, and it's important we use the same initial state, of course. And then you see the code words are just these numbers. They're really fixed length bit strings. I just wrote them in decimal to make it more human friendly. But you should think of these of all having, say, 12 bits. And there's leading zeros where the numbers are shorter. Is that clear? That was a question that came up on Campus Wire, so I thought I'd point this out again. All right. So how does the decoding work? We see a number, 67. And so we find the entry in the dictionary. That's the first phrase that we decode. That's great. And so here's it's written as a table, but it's producing the source code and what you add to the dictionary in one go. Just to have it nicely written up. So we decode this to C. That's the first part of the source text, and you will be able to read the source text down from here at the end. We can't do anything else. We should add C and the next character to the dictionary, but we can't do that yet. So we move on to the second code word, decode what that is. It's again a single character, so we read that from the dictionary. We find the A, and now we add a new phrase to the dictionary, namely the previous phrase plus the first character of the current phrase. So that's Y. Sorry, no, that's A. That's the new phrase. X is the previous phrase. That's C. And so we add X and the first character of Y to the dictionary. And that's what we do. Okay? And again, of course, we don't really store this as string. We can store it as one code word plus one letter. Uses less space. Okay, keep going like this for a while. So 78 is another single character letter. So we decode that. And now we have another round of a previous phrase, A, a new phrase, N. So we add an to the dictionary as shown here. Now in these simple examples at the beginning, x and y are single characters. But in the general case, x is any string, and what we add to x is the first character of y. One more, we decode the space, and we add previous phrase plus first character to the dictionary. One more, and then things first get more interesting. So we have the 129. That's one of the phrases we added. So it decodes to an. It's the first time we use one of these. So let me write one last time. Our previous phrase was the B. The new phrase is an. So the first letter of an is A, which means we add BA to the dictionary. And that's what you see here. All right. So just to the point where we see, OK, we have understood things. Now suddenly we run into this weird situation. The next coded word is the 133, which would be the next code to fill. But we haven't filled it yet. So we don't know what to do. We don't know what to decode it to. And it looks like this is a terrible dead end, which comes from the fact that the encoding is always one step ahead. And now in decoding, we never quite catch up. And so we can run into this situation. Fortunately, by just looking at this a bit more closely, we can resolve it. So again, problem comes from this lagging behind. And that might lead to the situation that we want to decode the code word that we're just about to fill after this round. So what can we do? We can have a close look at when exactly this situation can happen. And then you'll see that it's actually not a problem. So we're decoding the same phrase that we're now filling. And that means in the encoder also generated that phrase right from the previous step. It has to be like that, because otherwise the encoder would also not have had that phrase. So the encoder started with an and encoded that, and then added to the dictionary ana. And then ana comes again. That's exactly the situation. It can only happen like this. The encoder has a phrase, adds a new character, and then that new phrase directly appears one more time. But if that happens, we know that this an is the same as this an, and this a here is the same as this a here. So we actually know a lot more about this specific string. And in particular, we know that this C must be the first character of the previous phrase in this case. All right, so again, follow along the picture. We have an in the encoder previously. We encode that, but then we add the a and put that into the dictionary as a new phrase. And now it says the situation means we've now used that phrase as the next step. So the next phrase must be ana. And that's the next thing that the encoder encodes. So it uses this new phrase. And that means that this ana is the same as this ana. So the blue a always is the first character of x. So with this special case of just using the case analysis and substituting that here it's not the first character of y, but simply the first character of x again, we can resolve that case. So here's the code for that. It looks like a lot of text, but apart from this special case, there's nothing really complicated going on. We start with a dictionary. In this case, we don't need a fancy trie or any special data structure. It's just an array with strings or pairs of previous phrase and one character. And we initialize the first section with all the single characters in the alphabet. Then we have, as before, a variable for the next free code word. As a shorthand, we cache the next code word to decode. And y is this phrase that we're now decoding. Same name as before. And we have the source text. Initially, that's just the first phrase, and we'll keep adding to it. Now we iterate through the length of the coded text. We remember the previous phrase in X. What was Y last time is X now. We look at the next code word. And then if that code word is the special case, we're trying to use the code word that we're just about to write to the dictionary, then we know Y is of this special form. We know what to do. And otherwise, it's one that we added earlier, so we can look it up from the dictionary. Then we add that to our source text, store the new phrase. So this is the real Y that we decoded. So this is that's the phrase that we add to the next point, and it captures both cases now because we set Y here to this and advance this. I think the code is not too complicated after you've seen the special case. The rest is exactly as in the example coded down. So to finish off our example from before, if we're in this special case where we use exactly the previous phrase, we know previous phrase was AN. We're in the special case that we need the same phrase again, so we append the first character of that same phrase. That's our new code word, or new phrase for the text. So we add that to the dictionary and also use it right away. All right. With the key things out of the way, so if you have questions about the decoding, maybe we should do that first. If not, I'd like you to think about a bit about the extreme cases for this. Oh, kicked me out again. Okay, slider keeps reloading. I'll get there eventually. Well, lots of thinking time for you this time. Okay, there we go. Mm-hmm. Okay, in the interest of everyone at home, I hope it's just Slido that's slow and not our connection here. I think we've been well over 30 before, so let's wait a little bit. I didn't reset the answer, so I don't know how many we've had today. But given that you had a lot of time to think while I was fighting with Slido, let's pretend 30 is enough. And that means one more. Oh, okay. There we go. Let me dissect a bit why that's the case. So this is a question, in a way, first of all, a text that consists of just A's repeated hopefully is something like the best case for compression. It's as boring as it can possibly get. So we should, in a way, see this as the best possible case. What's, in the extreme case, the compressibility, or what compression ratio can Lempelsiff-Welch achieve if the text is as boring as can be. And so let's write a bunch of A's. Now let's start simulating what the Lempelsiff-Welch algorithm would do to see if we can spot a pattern. Initially, it'll fill its table with all the symbols in the alphabet. Let's suppose whatever A is one of these, right? So the first step, the first phrase we find is just the single A. We encode the code word for that, whatever it is. And then we add A plus the next character to the dictionary. That's how it always worked. So we add AA to the dictionary. And then we move on. Next phrase is precisely that AA that we just created, right? That's the longest match we can find. We encode that and store that plus the next character to the dictionary, which is 3 A's. And then want to guess why what happens? We find the 3 A's right again. So the next phrase will be these. And then we add a 4th A, put that in the dictionary, which is again what we find. So you can probably spot the pattern by now. If you decode this, by the way, we will always run into the weird case where we use the phrase that we just are about to add. So if you want to practice that and see if you got the cases right, this is a simple example to force the special case. Okay, so we always make the phrases one longer. What does that mean for the number of phrases? If we sum up the total length that we cover with phrases, then let's open, this runs to something that we don't know, but we want that this covers at least the length of the string, right? So if you put some specific number, k, that we don't know yet, if that inequality is fulfilled, then we have enough phrases to cover the entire text. And so this sum is, in asymptotic notation, let's write it on this side, is k squared over 2. Now I know you can probably work this out. You all know Gauss's little formula and so on. You can solve it entirely, but the point is, if you solve for k, then roughly the order of growth is root n. So that's why we get that. It's not super intuitive. You need to really think about some concrete example to see why that happens. If you just think about the procedure and I would have told you root n is the best possible, it feels like, why? There's nothing squarish happening. It's only through this indirect route. All right. So that's all for Lempelsiff-Welch. Let's briefly wrap up what we've seen. So there's a few bits and bobs before I come to the pro and cons. There's a few things from the presentation where you should say, hold on a minute. I promised that we use this fixed size alphabet, say 12 bits, which means the dictionary is a finite size. If I keep encoding things, I will eventually fill up the entire dictionary. I always add one more phrase. So at some point, I have to deal with the situation that the dictionary is full. And there's different options what you can do. Each can make sense. Depends on what you want to achieve and what the input looks like. If you have reason to believe that the text is overall repeating, then it might make sense to just increment the code word size over time. The other option, often used in practice because it avoids running out of memory eventually, is to just flush the dictionary, start from scratch. So you fill it up, and then you pretend you start from the initial state again. And indeed, most applications of zip and so on, they have a special code word where the encoder can say, I think now is a smart time to just abandon the dictionary, flush it, and start from scratch. And why would you ever want to do that on purpose before it fills up? You would want to do that if the text changes its nature. So if there's, say, if it's two documents, one in English and one in French, concatenated, then maybe there's not too much repetition in the French part branching back to the English part. And if you can somehow, with some heuristic, detect, say, you've always just used single letters for a while, then maybe it's better to just flush and start from scratch. Things like that people try to do in practice. From our side, it's just, we'll mostly in our examples, we'll just treat the case where you still have time, still have space in your dictionary. For a general implementation, you have to just decide what you want to do. All of these have their pros and cons. So this gets better compression, but might fill up your main memory because you keep adding to a dictionary. This avoids that, but if you flush the dictionary too early, then you may miss some repetition from far back. All right. The good part is that encoding, decoding all runs in linear time. And if you have space for the dictionary, you can even do it in streaming mode. You don't ever look back into the text, really. All you need is your dictionary. And that's why people use lempelsive methods also for transport layer compression. Now, good question. Which layer is this? I think it's at HTTP layer. So web traffic, you can automatically tell your operating system to compress the stream before it leaves the network, before it leaves on the network. And that this can be done while just reading the text once and outputting the compressed result. That's important for such an application. Okay. So we like the fast encoding and decoding, obviously, and that it works in this streaming way. It also works really well for many types of data that we seem to have in our world. And I've mentioned why before. It's just a lot is text-based in one form or another, and there's many human-friendly text tends to have small repeated parts that mean something to us. With a bounded dictionary, at least, if we do this flushing technique, we're somewhat local in the repetitions that we can catch. And even if you keep increasing your dictionary, you will be able to reach all the way back to find repetitions, but you make all code words one bit longer, which may not be a good deal in all cases. So then you can play more tricks like the first bullet. Take these code words that come out of that and try to compress that further with some other technique like a Huffman code. But if you keep stacking things up too high, it becomes tough to understand what's happening. So there's some slight negative part that capturing really long range repetitions doesn't usually work so well with lempelsive. I'm just mentioning this here because we'll come back to that question later. I want to summarize what we've seen so far because these are the traditional compression methods and the three most important ones we've seen. I don't necessarily want to read that out all again. It's basically repeating what I said on the discussion slides of the appropriate chapters. But as a little service to you, I summarized it. And there's a few comments on where it's used in what form. as I said before, none of these methods is used in isolation as the solution for everything. They're usually used in combination. And we'll come back to that as well. Any questions on these methods so far? Okay. I'll put the attendance code again in case someone needs it. I have a third part of the compression unit where the methods technically are not compression methods, but they are useful in compression by, in a way, transforming the data into a more convenient form. We'll see basically two of these, and both turn out to be effective in their own quirky way. I'll comment more on that later. So, to sum up the table from before, we've seen ways to exploit redundancy in various methods. If you have a character repeated many times, run length encoding captures that. If you have frequencies of the characters that are vastly different, some characters much more frequent than others, then Huffman's your guy to capture that redundancy. And if you have particularly long local repetitions, something like well, okay, don't want to go too deep into any specific cases, but some text that keeps repeating, like the shining text would be one. It's always the same sentence, so it's never far to reach back to the last repetition. Then Lempel-Sif methods work very well. If you apply these to all sorts of data that arises in application, it's sometimes super frustrating to see how blind they are to obvious redundancy, but obvious to you as a human. Some examples: if the repetitions are too far away, Lempel-Sif has flushed the dictionary and forgotten everything, so then it wouldn't work. If you have, say, a text with lots of A's in the beginning, lots of C's at the end, then overall A's and C's may be equally likely, have the same frequency, and Huffman wouldn't be able to exploit that. But in the first half, you should have really used a shortcode for A, and in the second half, a shortcode for C. Huffman can't really do that. So it would be nice to have that more locally, but it seems to get complicated to figure out a good way to do that. And of course, run length encoding is so restricted that there's many ways how to make it not work by just breaking runs. And still, if you have some pairs alternating, it feels like it should be a run, but it doesn't work with run length encoding as we defined it. And that's where text transformations can sometimes help. They at least broaden the range of texts, or the range of data sets that compression methods can find redundancies in. They're similar to our compression methods in that they have a source code and a coded source text and a coded text, and you can go back and forth. You don't lose anything. But the goal for them is to not directly reduce space usage. That's why they're not called a compression method. They're just there to set the stage for one of the previous methods to pick up the redundancy that's there. And so they're used as part of a pipeline. I think this becomes much clearer with a concrete example. So let's see our first one. The first text transformation is called the move to front transformation. And it comes from something that some of you may have seen. It's often, so this is like a little digression. Forget compression for a minute. This is a lovely little data structure problem sometimes used to introduce competitive analysis and online algorithms and things like that. If you've never heard any of these, don't worry. You don't need that here. It's just for context, and make the connection if you have seen it. The goal there is to have a self-adjusting linked list. Is just a linked list as you have seen it in our implementations for stacks. And it's unordered. So if you search for something, you have to start reading from the beginning and walk your way through the list. Now, the question is, what order should you keep the elements in? In principle, because it's unordered, any order is fine. But here, the goal is to make use of the fact that maybe some elements are needed more often than others. Or maybe if an element was used now, maybe it's needed soon again. Things like that. And so as a very simplistic model, you can say, let's pretend we have to keep it in a linked list. But when you access an element, you've walked through that list anyways, so you may as well restructure it while you're going. And in general, you can pay more and go further and restructure more. That's the game in the self-adjusting linked list world. Now, if that sounds interesting, I'm happy to give you pointers where to read more. All we need for here is the following strategy that turns out to be a relatively good strategy for this problem. It's very simple. That's what it's written here. Whenever you access an element, you walk through the list until you find it, and then you rip it out there and put it at the beginning of the list. And intuitively, it's something like a least recently used ordering. Right? The item you've just touched becomes the first. The next item is the one that you used before that, and so on. So over time, you ordered the list in this order of least recently used. Most recently used? I think least recently used is the cache eviction strategy. You sort the items by when you used them last. Very at the front. Okay, I think you get the problem. And so over time, the list somewhat automatically learns which elements are used more often. What does all of that have to do with compression? So let's come back to text. The idea that people had was, let's apply that to our source alphabet. So we throw our source alphabet in a linked list, and we apply this move to front rule. Whenever we encode, when we find a single letter, we find it in the list. We represent it by the index in the list that it had, but then we move it to the front. That's pretty much what it does. So that's just saying what I described. You find a new letter in your string, in your source text. You search it in the list, starting from the beginning, and use the position as the code word. Then you move that element to the front and keep going. So the code words now are integers. You transform it from some arbitrary alphabet to the integer 0 up to sigma minus 1. Let's see. Maybe let's do that first. So just to see if the idea is clear enough. Again, this is not a question that's supposed to be tricky. Just making sure that my hand-wavy explanation without a concrete example was enough for you. So the way to read this, here's the front. You have these letters in the list. So there's, I don't know, shall we draw these lovely diagrams? There's X, and then pointer to the next element Y, pointer to the next element Z, and so on. All right, now we access A. What does the list look like when we're done? Let's wait for 30 people again. 13 to go. All right, the spelling, how exactly you format things, that screws up the display a bit, but other than that, I think most people got it. Shall we wait till 25? Is anyone still working in here? Looks like not many. All right, 25. So let's see. There's a big blob for A, X, Y, C, B, C, and the usual. And that's the correct answer. So what you can do nicely here, okay, copy. Let's see if that works. This time it does. So we have that list before, and then after, what we do is we traverse, we walk through the list until we find the letter we want. That's A. Then we rip it out of this here, put it in the front. We wire this so that C still points to somewhere. And then if we read the list, it's A, X, Y, Z, B, C, and that's what the majority has voted for. Okay, so that's how move to front works. This time I'll start with the code here because I wanted to show how very, very similar encoding and decoding in this case is. We always start with the move to front list initialized with some order, and well, without any other options, just put the alphabet in sorted order. Then we start in the encoding. The code word starts empty. That's this epsilon here. Then we walk through each character in the source text. That's our character C. Then we find the position in our linked list, in the move to front list. So we walk from the front until we find it. That gives us a position P. That's the index, 0 based. That's what we store. And then we do the move to front step. For decoding, almost the same. We produce the source text, of course, not the coded text. We read one character from the coded text, and that's our position P. And we get the character by moving to position P in L. So in one you walk through the list and check what character you have, and the other you count down the index until you find position P. But in both cases, we do the same move to front step. All right. Let's see an example for that. Okay, I wanted to align this. That didn't work. Okay, let's see the example. So the first letter we encode is I. We find that in the list, it's at position 8 at this point. So that's our output. Now, before we move to the next letter, we rip it out here, put it in front. That looks like this. I is now here. Everything else shifted one position to the right. Next letter N, we walk through the list, find it at position 13. So that's the output. And then we put N in front of everything. There we are. That's our N. And everything else is shifted one position to the right. We do that again. E, we find it at position 6. That's our output. And we move E to the front. All right, we see how this goes. I think I can speed up the example. It's the same thing happening over and over. Now, I want to point out two things that might give you an intuition why this transformation is any good. If you look at these two F's here, so now I wish I would have properly put this one off below the other, but you may just make out what happens. If I have twice the same character in the source text, or in general a run, that translates into zeros in the coded text because I'm putting it at the front and then using it right away again. And then there's other things like this weird pattern, 3 C's. What would that correspond to in the source text? Well, it's the letters before this. That's this. If you look at these CIE, not so clear. Anything special about those? But if you look closer, it occurs earlier again. So a run like this occurs when there's a close repetition without reusing letters in between. But you can see there's some tendency, if the text has elements of boringness, then that can translate to zeros if it's a strict repetition. And a repetition of this kind might lead to runs of the same number. That's all I want you to take from this for now. So by itself doesn't help much. You have an alphabet of size sigma before, an alphabet of size sigma afterwards. But it turns out to turn things that we'll see after the next transformation into things that are easier to compress. Two comments about the output of this transformation are integers, so you still want to convert those to binary if you use it in compression. And of course, again, you have different options how to do that. The Elias code that we've seen in run length encoding has the nice feature that small numbers are represented with fewer bits. But of course, a Huffman code would always get you the best answer globally if you average out. One other thing I'd like you to think about is this deficiency of Huffman. I don't have this on the slide, unfortunately, but if you think about this text where I said, oh, it's very frustrating that Huffman codes don't seem to recognize that there's something to compress here. A bunch of A's and a bunch of C's. If you feed that through the move to front rule, you'll get some arbitrary letter, but then zeros. And then you get some arbitrary number and then zeros again. Now this is degenerate, of course, with all the zeros. You don't usually have that. But I want to point out that you have zeros and zeros. It didn't matter what the repetition is. So in a way, move to front manages to get different frequencies of characters down to the same numbers. Here we had lots of A's, here we had lots of C's, yet after move to front, they both correspond to lots of zeros. That's at least one step in the direction that might make a Huffman code after this more effective. Okay. All right. Let me teaser very briefly what this is about, and then we'll properly cover it next time. In the next subsection, I want to introduce the most exciting of these transforms that has just celebrated its 20th century as 20th birth. No, that can't be 30th birthday. And it was initially deemed as a nice theoretical idea, but completely impractical, and we'll never have enough memory to do that. And now it's used all over the place and is one of the staples of compression methods with some really nice magic properties in a way. And that's the Burrows-Wheeler transform. let me skip that part and I'll cover that next time a bit. I want to just introduce briefly the definition. We need the notion of a cyclic shift, which is just if you write a text around the circle, there's one way to normally cut it, but you may as well cut it somewhere else and then you get a different cyclic shift. Or it's a way of you shift all characters to the right, and those that fall off the end you put in the beginning. That's that. If we put an end of word character in, old trick from before, then we can always recover the original string because the end of word character tells us where the original step was. And now the Burrows-Wheeler transform is the following absurd definition. You take a text at the end of string marker, take all cyclic shifts. So you take the text, original text, shift it by once over, shift it by 2 over, and so on. And then you sort this list of strings. Fine. And then from this list of strings sorted, you take the last column. And that column is the Burrows-Wheeler transform. And here's an example for this nice text. All the cyclic shifts, then you sort them, and that's the BWT. I think if you just see this definition, it doesn't make much sense why you would do that. And also, more excitingly, that this is invertible. We sorted something in between. We sorted all the cyclic shifts. And normally if you sort, the original order is lost. But for the BWT, it's not. You can invert, you can get back the original text from just this last column in the sorted matrix. But that we'll have to wait till Wednesday.